Hi, I'm Ben-Yaakov. This presentation is entitled The Hidden Secret of the Bidirectional GaN-transistor-based Single-Stage AC to DC Converter. Well, it's a long title. Now, recently, a number of manufacturers, including Navitas, introduced a bidirectional GaN transistor. I'm showing here the Navitas version. It is a one element which functions like two transistors back to back, two GaN transistors back to back. We have here the source, the gate of one side, and then the source and gate of the other side. So the analogy is actually like a two transistors, in this case silicon transistor, back to back. And obviously we are talking here about the GaN technology, and it is a one integrated device which has the two inputs. And of course, it'll be faster than the silicon. And the fact that it is one device can be packaged in one package will make it handy and hopefully more economical. Now, as far as application, Navitas is showing, or claiming, I should say, that you can improve a lot the classical topology of a power supply, which at high power will consist of a power factor correction, a DC link, and then a DC-DC converter for either stabilizing or stepping down the voltage, let's say to 48 volt. And of course, you can improve on it first by replacing the transistor, silicon transistor with GaN or silicon carbide. But here, what Navitas is saying, that this bidirectional GaN element here or device can be used to build a new single-stage power supply, combining the power factor and DC to DC, and moreover, it eliminates the DC link capacitor. This presentation is actually related to this statement here. I'm not going into the structure of the switch or comparing it to similar devices by other manufacturers, but rather to elaborate on this sentence here. It eliminates DC link capacitor. So here is what the CEO of Navitas has to say on the subject.
With GaN BDS applied to single-stage converters, so what we call single-stage BDS converters, this is all about to change. The entire first PFC stage disappears. The electrolytic capacitors, DC link capacitors, disappear.
And here are some examples that Navitas is showing. Here is a full bridge with the bidirectional switches. By this bridge can accommodate positive or negative voltage. So therefore, you don't need a rectifier. So you can sort of chop the input, and then this is fed to a resonant network, and then rectified here. And of course, this could be active bridge, so it could be bidirectional. Well, they're showing here a capacitor, which I guess they're implying that this is a small capacitor. Now, it turns out that this is not a new concept, and there are quite a number of papers. I'm just bringing two of them. One is an older paper, and what we see here is this is a bridge which is just a polarity changer, that is a switching polarity such that the polarity will be always positive here. So these are regular MOSFET, not bidirectional, which cannot tolerate, of course, a negative voltage. So we have here a positive voltage. We have here a bridge. And again, this pulsating voltage is chopped and then fed, in this particular case, to an LLC. And then we have a synchronous rectifier at the output. And in here, they're showing a filter output, and this will be the load. Okay. There is another example here with two transistors, which are back to back. And this can be replaced, of course, with this bidirectional transistor or element that Navitas is showing. This is a half bridge. Again, the idea is similar. This is chopping the AC here. These are capacitors for high frequency, just for the switching, and feed it to this coupled inductor. And the leakage inductance here is actually used to control the magnitude of the current that will be passing to the output. And then here we have the rectifier. And of course, we have a bulk capacitor here, the output. And in this particular case, it's like charging a battery. Here, there is an inductor for blocking the AC current. And then we have basically a DC here feeding the battery. So what is the story behind this single stage topology? Again, the conventional approach is power factor correction, bulk capacitor, DC to DC. Now, if we are combining these two, which we can in different ways, there are many ways to do it, then we still need a capacitor. I'm going to elaborate on it in the next slides. Now, you can have a capacitor or you can have a battery. Now, if you have a battery, then you might have a problem that the current will be pulsating. Why is this? Well, in a single-phase system, the input power is pulsating. It's not continuous because we have a voltage of a sinusoidal waveform. And if there is a power factor correction circuitry here, then the current will also be sinusoidal or close to sinusoidal and in phase. So when you multiply two sinusoidal waveforms, here it is, you get a pulsating power coming in from the AC line. Now, load usually needs a constant power. Now, this pulsating input power has an average, and this is what you want to feed to the output. But we have here excess energy coming from the line, and here there is a missing energy. So we need a storage element, and this will be a capacitor, to store this excess and then to deliver it when the power coming from the line is low. So there is nothing you can do about it. This is physics due to the fact that you have a pulsating power in, and if you want a constant power out, you do need a storage element in between. Now you can have it between two units, or you can have it at the output, but you do need a storage element. So if you put a battery at the output, you may not need a capacitor, theoretically. Now the voltage of the battery is constant during a certain instant of time, and then if the input power is pulsating, this would imply that the current to the battery has to be pulsating. This is not good because the RMS is high, so it's causing heating. Also, the peak current could be very high. So this is not recommended. It's not recommended to charge a battery with a current waveform of this profile. On the other hand, if you need a DC at the output, like say in a server, you do need a capacitor. Now the capacitor will pass the AC current, which is of twice the line frequency, 100 hertz or 120 hertz. And then there'll be some residual ripple depending on the size of the capacitor. Now the textbook equation for this capacitor, the size of the capacitor that you need, is this equation here. We have the output power that you need, the line frequency, the voltage ripple that you allow, this will be in peak to peak, and the output voltage. So if I take an example of a 1 kilowatt unit, 400 volt output, 50 hertz, and if I allow a ripple peak to peak of 10 volt, I need a capacitor of 800 microfarad. Of course, there are some methods of boosting up the voltage and therefore using smaller capacitor, but this, of course, entails an extra circuitry to do that. Now, if there is a need for 48 volt, lower voltage, and say in this case you allow a ripple of 1 volt peak to peak, then you need a 67 millifarad if it is at the output. So this is the reality. So when Navitas is saying
the electrolytic capacitors, DC link capacitors, disappear.
So this is not very accurate, to say the least. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest. Thank you very much.